Hey everyone, how are you today? It's the start of a new week. It's a Holy Week. Hopefully you had a good and restful weekend. We only have 4 days of school this week, and for chemistry, what we're going to do is we're going to do a lab and a lab report, and that's what you're going to do for the whole week. There won't be any other assignments. So hopefully this will be a little lighter in terms of your overall workload. So what you need to do today is watch the video that I'm going to do in terms of the lab and do the procedure for you. You'll collect the data, and then Tuesday you would be working on some of the calculations. I think what I'll plan on doing is maybe having a Zoom conference on Tuesday that will allow you to come in and chat if you want, if you have some questions. If you're figuring out the calculations on your own, then there won't be any need to do that. And then Wednesday and Thursday, you'll have the rest of the time to do a lab report, Google Doc lab report, like what you've been typically doing for a lot of our labs. And then we'll have it due sometime Thursday, and then you won't have anything to do the rest of the week, and you'll be able to enjoy the Easter weekend the best you can without having to worry about any other chemistry assignments. All right, so let's get started right away. The lab we are doing today is called Molar Volume of Hydrogen Gas. And you should find this document posted for you on Google Classroom. It's probably already on the Friday post. I'm doing this a little in advance, but I think I plan to post it on Friday so you can do a couple of the pre-lab questions. There are 4 pre-lab questions for you, and those you should be doing before you do the lab. So if you haven't done these questions yet, you should be doing them now. Stop the video, come back later, watch the rest of it if you haven't done these 4. Okay, so make sure you do these. These should be in your final lab report when you get done. Okay, so the procedure that we're using today is, for the most part, what's in the lab handout. However, there's going to be some modifications because of the equipment that we have here. So you don't really need to follow the procedure. You can look it over if you want, just to get a feel for what we're doing. But as long as you're paying attention to visually what we're doing here and collecting the data, that should be good to go. Okay, so the purpose of this lab is to be able to determine what is the molar volume for hydrogen. Now, think back to what that term would mean, molar volume. It has something to do with moles, something to do with volume. So what the molar volume is the volume of 1 mole of that gas, of hydrogen gas. And so that's what we're going to try and determine today. We're going to try and figure out what is the volume of 1 mole of hydrogen gas. Now, using the equipment that we have, I can't measure or produce a mole of hydrogen because that'd be an awful lot. So we're going to produce a smaller quantity, and then we're going to proportionalize it and scale it up to a mole and see what we come up with. Okay, hopefully you're understanding by now that our gas laws tell us that when we measure the volume of a gas, we have to pay attention to some other variables too, namely pressure and temperature, because those 2 things affect the volume, right? If you collect a gas at a certain volume or a certain temperature, then it's not going to be the same volume as if you collected it at a different temperature. So we have to use our gas laws to help us proportionalize that. So we'll be using the combined gas law as part of our calculations here. We're also going to make use of Dalton's law, which was Friday's lesson. And hopefully you understand that Dalton's law tells us that when we collect a gas and it's a mixture of different gases, the total pressure of that mixture is simply the individual pressures of the gases added together. One of the things that creates an issue when we try and do reactions producing a gas is that we have to find a way to collect the gas. You can't just put the gas in a container, a beaker, or a test tube like you do a liquid and solid and go weigh it, because gases just dissipate, right? They go throughout the room. So we have to use our water displacement technique, which you also learned about on Friday. So we're going to collect the gas underwater. All right, that doesn't mean I'm going to be underwater. All right, but we're going to do the experiment underwater to allow the gas to bubble through the water and collect it. That way the water acts as a trap and doesn't allow the gas to escape. However, when we do that, because of the nature of the gas bubbling through the water, water evaporates into a gas. So in my tube, I'm eventually going to have some hydrogen gas, but I'm also going to have some water vapor in there because the water evaporates during the experiment. So the total pressure that I get here is really the pressure of those two gases, hydrogen and water vapor. So I'm going to have to use Dalton's law to help us determine what is the pressure of just the hydrogen portion of that mixture of gases. And hopefully you learn on Friday a little bit about how that happens. Okay, so we're going to be using combined gas law, Dalton's gas law, to help us find the molar volume of hydrogen gas. All right, so let's get started a little bit here. The reaction we're going to do to produce our hydrogen gas is magnesium, our piece of magnesium that we've used in the past, and some hydrochloric acid. Okay, so what I want you to do while I'm setting this up, I want you to write out the balanced equation for a reaction of HCl and magnesium metal. So see if you can write that out while I'm trying to set this up. Okay, if you need to, you can stop the video, but I think you can probably do that while I'm setting this up because it's going to need to do a little bit of a setup here. So the first thing I'll do is I'll pour some hydrochloric acid into my container here. And the container that I'm going to use is a burette, right? We've used a burette in the past to help measure out a certain amount of liquid, okay? Today what we're going to do is we're going to use this to help us capture the gas. So to do that, because this end up here is open, what I'm going to do is this is going to be inverted eventually so that the gas can move up to the top, okay? And the water will be on the bottom, will act as a seal on the bottom, and so I'll be able to fill this up. Now, one of the problems with using this particular piece of equipment for this experiment is that up at the top, I don't know if you can see this or not, but there are marking lines, right? But then they stop, and then there's this little space up here that's not measured. Because when we use it as a burette like this, we don't go past that 50 mark. We don't need to know that. But today, since I'm inverting it, the gas is going to go up. There's going to be some gas that fills that space. So what I'm going to do now is I'm going to try and determine what is the volume of space there because we're going to have to add that onto our measurements later on. Okay, so hopefully you're writing out your balanced equation. So what I'm going to do here before I put the hydrochloric acid in is I'm going to put a little bit of water in here to fill up that space. I'm going to use a pipette to do that. So I've got a sample of water over here. All right, I've got 1 milliliter of water. And I'm going to fill up that space. I'm hoping it's not more than 1 milliliter. I don't think it is. So I'm going to put in a half a milliliter and see if it fills it up. Not quite. I'll put in a little bit more. And I'm almost there. Probably got another milliliter. I'm going to probably overshoot this a little bit, and I'll show you how we'll deal with that. Almost, it is going to be almost 1 milliliter. In fact, I'm going to put all that in and see where that ends up coming up. So I ended up, I don't know if you can see this real well or not, but if you can see I'm a little above 50, and it looks like I'm about, I'm going to say 3 milliliters above 50. So what that means, or 0.3 of a milliliter above 50. So what that means is I added 0.7 of water to the bottom of that. And I'm going to write that down. 0.7 of a milliliter, which is the space that I'm going to have to include later on in my gas measurement. Because again, I'm going to turn it upside down. I'm going to use up that space with the hydrogen gas. All right, so hopefully you got your balanced equation. Hopefully it looks something like Mg plus HCl produces H2, subscript 2 because hydrogen's diatomic, right? And MgCl2. So Mg has a +2 charge, Cl has a -1 charge, so I'm going to need 2 Cl's in that magnesium chloride, which means to balance the equation, you have a coefficient where? Hopefully you realize you had a coefficient 2 in front of the HCl on the left side. All right, so that's your balance equation. So we actually used this reaction a couple of weeks ago, and we paid attention to how much magnesium was there and how much HCl was there, and used it as part of a limiting reactant experiment. Today, we're going to focus on the gas that gets produced. So it's the same reaction that we've done. We're just going to focus on the gas part. Okay, so I've got some hydrochloric acid here, and I'm going to add. The amount of hydrochloric acid is not critical as long as I know I have it in excess. And I've got a 3 molar solution of hydrochloric acid, and as long as I have at least 10 milliliters of acid in there, which I have almost 20 milliliters. I'll have plenty of acid in there, and that'll be the substance in excess that will ensure that all of my magnesium reacts, okay? The magnesium, it's a very small strip, okay? And so I need to know how much magnesium I'm adding. If I would go put this on a balance, it doesn't weigh that much, and it's going to be difficult for me to get an accurate measurement, okay? It's only going to weigh in the range of about a few hundredths of a gram. Now, I do have one balance in the back. I think we've pulled it out once before. That measures to a thousandth of a gram. So that would give me 2 significant figures. However, there's another way in which I can measure the amount of magnesium here and get 3 significant figures. So what I did is I measured a long strip of magnesium, 100 centimeters, okay? And I determined what that weighed. It weighed 1.426 grams. I'll show you that in a minute. And then I'm measuring the length of my strip of magnesium. And using a standard ruler like this that's measured to centimeters and then tenths of a centimeter, I can also actually estimate to 100th of a centimeter pretty accurately. And I estimated this mass to be 3.39 centimeters, okay? So I'll show you my data table here. You can get this down. So 100 centimeters of magnesium, which has 4 significant figures in it, weighed 1.426 grams on my balance. So I used that information. I made a proportion with that with 3.39 centimeters. You'll actually have to do this in the first calculation. And I determined what the mass is. So this is a calculated mass based on these 3 pieces of information. Now, if you notice, that gave me 1, 2, 3 significant figures because I had 3 significant figures here and 4 in each of those. So this becomes one of the fewest number of significant figures, so I can get a mass of significant figures of 3. If I just put this on my balance, I would only have had 2 significant figures because my best balance only measures to a thousandth of a gram. So by measuring a larger piece of magnesium and proportionalizing down, I'm able to still maintain 3 significant figures. That'll become important because that'll help us get better data later on when I want to know what the molar volume of hydrogen is. Okay? All right, so let's start our reaction. I've got my magnesium here. I'm going to put it in my test or my burette here. I'm going to wrap it around this coil of copper wire. And this becomes helpful because magnesium is lighter than the water and acid that I'm putting it in. And so it will tend to like to break off. All right. And so I'm going to try and do this in a way that I can keep it on there for a long period of time. And I don't know how well it's going to work, but we'll see. All right. Because I don't want to bend my magnesium so much that it's going to fall off. Okay. All right, so the other thing I need to do is I need to fill up my burette here with water because I've got to get rid of all the air that's in here. So remember, we're going to do the experiment through water displacement. So let me fill this up with some water. to get it all the way to the top. Almost to the top. There we go. All the way up to the top. And then I'm going to take my stopper with the magnesium strip on it, right? I'm going to put that in here so that I don't have any air bubbles. Okay, so I've got hydrochloric acid down here, and hydrochloric acid is more dense than water, so it stays down here. So I don't have the reaction working yet. But what I'm going to do is I'm going to turn this upside down, and the hydrochloric acid will float down. I'll try and show you what that looks like if I can get the camera close enough to do that. Okay? All right, so let me turn this around here a little bit. And I'm going to put my finger on top. I'm going to quickly invert this into a pool or beaker of water and reattach. And what I'll do is I'll try and get the camera close enough to see, or to let you see, if you can see some of the acid floating down. I don't know how well you can see that. So the acid is heavier than water, so it's floating down all the way to the bottom, and it will eventually start to react with the magnesium gas. Okay, so now this is going to take a little bit of time, so eventually I'm going to cut the video and then come back just so that you don't have to sit here for 10 minutes watching it. Before I do that though, if you remember, we said the volume of this gas is also dependent on temperature and pressure. So I've got a thermometer that I'm going to stick into my container here and turn back my LabQuest on, because it just went to sleep on me here. See if I can get it back on for you. There we go. Okay, so I've got a thermometer, I've got a gas pressure sensor in here, and so this is something you're going to need to write down data for. I've got a temperature of about 18.7 degrees Celsius. So I'm going to write that down for my data, 18.7 degrees Celsius, and my pressure is hovering right at 100 kPa. So 99.98, 99.99. Let's just write down 100, because I'm only going to need 3 significant figures anyways, and so that's going to round up to 100 as it is. So write down 100.01 kPa. Now, what I'm thinking though is that when we do our calculations later, it'll be easier to do this in atmospheres. So let me see if I can change this to atmospheres real quick. On the Chromebook, I'd know how to do this very easily. On the LabQuest, not so sure. Oh, change units. ATM. All right, so now it's in ATM. So let's write that down. It's 98.68, 98.69. So we'll round that to 0.987. 0.987 ATM. That way, when we use our combined gas law, we can just use 1 ATM as our standard pressure and temperature. You'll see how that works. Okay? All right. So you should be able to see now quite the reaction going on. Okay? Lots of bubbles. Hopefully you can see that. And up at the top, you can see that there's gas being filled into the burette. So that's our hydrogen gas. Keep in mind that because of all the bubbling, water is also evaporating into that space. So I've got a mixture up here, hydrogen gas and water vapor. We're going to have to use Dalton's law later to determine the pressure of just the hydrogen gas. Okay, so this is maybe about halfway done. So what I'm going to do is I'm going to turn off the video now and come back and show you what happens after the reaction. All right, so I'll be back in a few minutes.